Today, myself and Johan are going to be talking about just getting started with our respective products that work together, FreeRTOS and FreeRTOS+Trace. You want to introduce yourself?
Yes, my name is, as you can see, Johan Kraft. I'm founder and CEO of a company called Tracealyzer, and we develop tools for visualizing traces of embedded software. And one of these tools is for FreeRTOS that we're going to use today.
Okay. And my name is Richard Barry. I have several hats. Firstly, my company develop, maintain and distribute FreeRTOS. We'll talk a lot about that, obviously. There are commercial versions as well, I should mention. We license the product to a company called Wittgenstein. They provide exactly the same product under a commercial license and also a safety critical certified version of the product. Right, there is a lot to get through today. A full training course would normally be 4 days, 3 days, depending. So this is really a getting started introduction, and hopefully what we go through today will give you an overview of how to use both FreeRTOS and the trace tools, which really helps your use of FreeRTOS, especially when it comes to application design and optimization and debugging and that sort of thing. But we're really just going to scratch the surface. So the first thing is just a bit of terminology and to explain a little bit about real-time kernels. What are we talking about? Well, multitasking. These diagrams here, this is really just to introduce the diagrams. So we have time moving along the bottom axis there, and the coloured lines represent different threads of execution. So I'll probably use the word thread and task interchangeably. In the FreeRTOS world, we normally say task rather than thread. If you're from the Linux world or something like that, then you get the thread model is, and the process model means a little bit more. So we try and avoid that terminology and just say task. So we have different tasks running, and the coloured line shows at any particular time which task is running. So what we want to do is give the illusion that all the tasks are running at once. Now, if you only have a single core, then of course there can only actually be one task running at once. So the scheduler is the bit that chooses which task to run when. And the difference between a normal OS and a real-time OS is basically whether the system can promise to act determinately, then it's real-time. So if it can say, when this event occurs, by a certain time, I will guarantee to perform some action, then that distinguishes a real-time operating system from a general purpose or multi-user operating system. And that's really the only difference. A lot of people think it's to do with speed, whereas in fact it's to do with determinism. But this is just terminology, right? We can argue that either way. So in this class of operating system, how do we get that real-time behavior? FreeRTOS, like most systems in its class, use what we call a prioritized preemptive scheduler. And that means the scheduling algorithm, the piece of software that decides which task to run when, will always choose the task which has the highest priority. And it's the application writer who decides which tasks have high priority. Generally, in a real-time system, you'll only have a few requirements that are genuinely real-time. The rest of them are a little bit more squidgy, what we might call soft real-time. So we've got the concept here. We have low-priority tasks, medium-priority task, and a high-priority task. This diagram, same concept. Time is moving along the left. Low-priority task is running. There's also a medium-priority task, which is blocked. Blocked means it is something preventing it from running. It's waiting for something. Because it's blocked, the scheduler will choose the low priority task to run. When that unblocks, whatever it's waiting for has happened, the scheduler will start running that task immediately. And this task here, although it's still ready to run, it's not waiting for anything, is what we call preempted. The application writer doesn't know anything about that. it's just writing a sequential piece of code. That task runs, it has a higher priority. When that task blocks again, we now have, in this diagram scenario, we have two tasks of equal priority. And what the scheduler will do then is it can't choose which one to run because they're both the same priority, so it will time slice between the two. So it will actually run both of them for a short period of time. Just following the same concepts, high priority task at some point becomes able to run. Now we have these two tasks that are preempted. That one blocks again, and those two tasks start time slicing again. Does that make sense? I'm afraid we're going through this rather quickly. That's a necessity because we only have 2 hours, but obviously if anything is not clear, then during the labs or something I can go over it again with people. Implied in that then is the fact that a task has a state. So here's a little state machine. Now when the task was actually running, it's in the running state. So when that line was actually coloured in, it's in the running state. When it's waiting for something, we say it's in the blocked state. And if it can run, but it's not actually running, then it's ready to run. So you can see tasks move through this state machine. When it's running, it makes a blocking API call. In the labs, by the way, and during the talk, we'll mention what can block a task and what makes it run. So we'll come back to these. Makes a blocking API call, moves into the blocked state. Very importantly, when it's in the blocked state, it's not using any CPU time at all. When the event occurs that it's waiting for, the scheduler will automatically move it from the block state into the into the ready state. And you can see there that while there is only one task per core that can be in the running state, there can be a pool of tasks that are in the ready state, and the scheduler will choose which one to move into the running state. So that's very, very quickly what a scheduler is. Now we'll talk a little bit about FreeRTOS, its market position. It is by far and away the most dominant OS on the market for this class of processor. So we'll look at the class of processor as well. You can see in the surveys here, you've got Android and Linux, which are completely different classes. They're great big MPU microprocessor operating systems, and FreeRTOS is up there with Linux and Android as being used or being considered to use in applications. We partner with all the different semiconductor companies you could possibly imagine. Actually, I think other than Toshiba, we don't partner with them. So the type of system it runs on, well, it's very difficult to quantify what these axes are here. So processing power. So down here you've got a 4-bit, old-fashioned 4-bit processor. I say old-fashioned, still use them all. And up this end you have the latest Intel server-style, massive, great big processors with 8 cores on them or whatever. And then we have applicability. So if you've got a very small processor, you're not going to be writing complex applications, and also you're not going to have that much flash or RAM available, so you're very rarely, or if ever, going to use a preemptive scheduler anyway. At that end, you've got Windows and Linux and Green Hills products and Wind River products and that sort of thing. And FreeRTOS really fits in the middle section. So it will run on 8 bits. I have to say, is it really worth it? Low end 32 bits, Cortex M3, PIC32, some of the MIPS processors, that sort of thing. And then up to Cortex A9, dual core A9s is about where it stops. Licensing, it is free. The clue is always in the name. Someone will always say at the end, but how much does it cost if we use it in a commercial application? It's still free. There is a commercial version available. If you want to buy the commercial version, we don't actually sell it ourselves. We license it to Wittgenstein and they'll sell you it. But what you get for that is legal indemnification and dedicated support, although FreeRTOS is supported itself, but through a forum. We support it directly through the forum. Everything we do removes any problems people have using open source code. So one thing in particular of note is there is no risk of IP infringement in it. It's what we call moderated open source. So if you contribute code back the other way, then it's made publicly available, but it's not included in the official code. So that way you know that it's clean. So OpenRTOS is effectively the same product. In fact, it is exactly the same product. It's just licensed differently. There's a large ecosystem around FreeRTOS. I mean, it's growing all the time. I was looking at the statistics just before I came out here, actually. And it's quite frightening that it still seems to be on a very strong trajectory upwards. This is the tool we're going to be using today, which is Johan's tool, the Trace tool.
We have a family of tools called Tracealyzer. This is Tracealyzer for FreeRTOS. And it looks like this. It allows you to record and visualize task scheduling, as like the diagrams Richard showed, but also calls to the FreeRTOS kernel, for instance, for sending messages to other tasks or locking a mutex or something. But you can also use it to log events in your application code, just like a printf, but it's many times faster, so it doesn't affect your timing so much. And you can even log interrupt handlers if you like. This is not open source, it's commercially licensed. It's developed by my company, Tracealyzer, and we will use this to illustrate the labs today.
So a task is just a C function. It has to have this prototype, so you can pass in a parameter, and we will see the parameter being used in the lab. And it's an infinite loop. So when you create a task, normally, well, I say normally it's an infinite loop. It will have a piece of functionality which it is performing, and it does it over and over again. In FreeRTOS, if you want to exit a task, then you have to delete it, and you can do that by calling this function at the end. Null just means delete the calling task. Otherwise, you could say delete the handle of a separate task. So the naming conventions here, either you love it or you hate it. It's prefixed with the return type, in this case it's a void function. Task means you'll find it in the task.c source file, and delete means, strangely, delete a task. So all the tasks we look at will have this prototype and will be structured like this. So creating a task is defined in task.c and it's create. This is why I say it's the most complex one, because of the number of parameters here. On the previous slide, we defined a function called a task, and this is the first parameter. So that is, we're passing in the task that we want to create. We give it a text name. That's useful for debugging, like with the trace tool. The kernel doesn't actually use that itself. It just allows you to, it's a bit more human-friendly when you're looking at debugging. Every task has its own stack. So you have to say how big you want the stack to be, and that's the parameter we pass in there. You will find this minimum stack size is defined in the, it's actually part of the demo applications. So each FreeRTOS port comes with one or more demo applications. So if you want to start using it, just like the labs today, you don't have to start putting the project together. You can just download the source files. There's a quick start guide on the website. Find the project that you need, open the project, and you're away and running. In that project, you will find this minimum stack size, which is the only place the kernel uses that really is to set the size of the stack of the idle task, which is a task automatically created. We'll see it in the lab. When you look at the traces, you'll see the idle task. And that's created automatically, so the kernel has something to do when all the other tasks are blocked. And you can just use that to put the system into a low power state if you want, so just turn everything off. This is where we pass in the parameter. Again, we'll use that in the lab. The priority of the task. We like to keep things logical, so the 0 is the lowest priority, 1 is above 0, 2 is higher than 1, obviously, and it goes up to a maximum which is defined in a configuration file, which again we'll look at. And here you can pass out a handle to the task if you want. We've already seen that call to task delete. If you wanted to delete another task, you would have to have the task's handle. If you don't want the handle to the task, you can just pass in null there. So very, very simply, this is like the embedded systems equivalent of Hello World. We're going to toggle an LED. So here we have a little flow chart, and we are going to wait until it's time to toggle the LED, and then we're going to toggle the LED, and then we're going to come back and wait again. The thing to note about this is it's just a sequential piece of code. Now this is obviously over simple. You would never use a kernel really to flash an LED, but if you were to do this in, say, a foreground, background or superloop type of application, you can see that built into your superloop you would have to have the timing information. What we're going to do with the kernel is actually allow the kernel to take care of all the timing for you. So our very, very simple LED flash is a very small sequential piece of code. So coming back to the state machine, we're either going to be in the running state or in the ready state. Now, if we're running this as a FreeRTOS task, what we want to avoid really is polling. So you can see here we have a very simple wait function. We're going to say we're going to wait, and we're just going to loop around this doing nothing until the time reaches the next toggle time. So we're just going to sit there spinning around in a loop in our task. And what do you think the problem with that might be? Exactly. You can't do anything else. Anything which is in a lower priority task is never going to run, because we're going to be in the running state, and we're going to be in here spinning, spinning, spinning. There's nothing to do, nothing to do, nothing to do. Oh, it's time to flash the LED. Flash the LED. Come back here. Spin, spin, spin. Nothing to do, nothing to do, nothing to do. Extremely inefficient. So what we want to do is use the kernel to make that more efficient for a start. And the scheduler might occasionally put you into the ready state to run higher priority tasks, but the important thing is you're never going into the blocked state. If you're not going into the blocked state, you're not using the kernel properly. So what we want to do is replace that busy spin with a call to a delay function. There are two task delay functions, so again it's defined in task.c, and it's going to delay, and that will delay a certain amount of time from the time you called the function, and the task delay until will delay until a fixed time in the future. So that's periodic, that's an absolute time, and that's relative time. So now we're going to flash our LED, we're going to call task delay. We know we don't want to flash it again for another 200 milliseconds or whatever, and the scheduler, because we've called that function, knows we've got nothing to do for 200 milliseconds or whatever time, and it will put us into the blocked state, put that task into the blocked state. When it's in the blocked state, it's not using any CPU time, so lower priority tasks can then execute, and that's the important thing. When the event occurs, in this case it's a timing event, an interrupt tick, the scheduler knows that 200 milliseconds is over and will move us into the ready state, move that task into the ready state. It can now do something. It wants to do something. In this case, it just wants to flash an LED, but there is something for it to do, and it's then available for the scheduler when it's the highest priority task to move it into the running state, and then it flashes its LED. Lots of software to flash an LED. Does that make sense? Okay, so In the first lab, we are going to look at doing just this. We will have some tasks with busy loops, and then we'll add delays, and we'll use the trace tool to visualize what I've just explained.
Yes, this is the board we're going to use for the lab. It has been donated for this workshop by Apple. It's not the very latest board, but it's a really nice Cortex M4 board with an integrated debugger. Has 128 kilobytes of RAM, plenty of flash. We're going to use Apple Studio, the latest version, 6.2. This is a free development environment. And we're also going to use FreeRTOS+Trace 2.6 version. We're very shortly coming out with version 2.7 that also runs on Linux and has some other improvements, but it's not quite ready yet, so we have to settle for 2.6 now.
When we open up the projects, in fact, you can open up the projects now. I think I have it on here as well. This is the standard Atmel Studio file structure. You'll see the FreeRTOS files are just these files here. So it's very, very few files that you need. And then we have the trace recorder files are underneath. Again, very few source files to add in. So every FreeRTOS project will have a configuration file called freertosconfig.h. One of the things this is just a subset of parameters you'll find in here, but one of the things on here we have is the maximum priorities. So the total available number of priorities is a configuration file setting that you control. There is no practical limit. You can set that to whatever you want. And you can run as many tasks at the same priority that you want as well. So there's no limit on the number of priorities other than the RAM you have available in your system. And there's no limit on the number of tasks that can share a priority. There are a few things in here like checking for stack overflows. There are several features in the kernel that are there to help you with your application development. One is checking for stack overflows. We said every task has its own stack. Stack overflow is a very common source of a problem. Obviously, the more features you put in to check your code, like asserts and stack overflows and that sort of thing, the bigger it will get and the slower it gets. And importantly, down at the bottom here, if you're using the trace tool, then there's a header file you can include at the bottom, and you can set this use trace facility to 1. So the projects that you have this in there already.
I just want to explain a bit more about FreeRTOS+Trace. What you see here in this main view of this tool is a vertical timeline showing the scheduling. You can show the scheduling in different ways using these buttons called view modes. In this mode, we have one column for each task, and these labels here on the right side are calls to the FreeRTOS kernel. For instance, task delay until here. But there is also events like send message to a queue, etc. And you see that they're color coded. The white ones are operations that succeed directly without changing the state of the task to blocked, for instance. The red ones are blocking calls. That means, for instance, that you try to write a message to a queue that is currently full, or you're trying to receive a message from a queue that is currently empty. Then the task will become blocked. Rachel will mention this later, how the theory behind this. And you get a red label. And the green label are the corresponding wake up of the task when the blocking ends. And there are various features in this tool. You can, for instance, connect the green label with the red labels to find the corresponding place where blocking begins and ends. And up in the view menu, you find a lot of different views giving other perspectives of the trace, such as the CPU load over time. You can plot data from the application and various things. But as I meant, the important thing here is that you have a vertical timeline showing task scheduling, labels. You have task names here. The colors are assigned from a color scale based on priority. So red colors are high priority and the blue colors are low priority. And whenever you click on something here, a label or one of these fragments, as we call them, you get the information up here. And here is also a filter that allows you to select what you want to view, what tasks or what kernel calls, for instance. Yes, so to use FreeRTOS+Trace, first you have to include those files that Richard mentioned previously in the project, and then you have to call these functions. This sets up the data structure for the tracing. This is software generated trace. We use a RAM buffer to store the events. The events are encoded quite efficiently, so even on a small microcontroller you can still get a decent trace. And then the trace start activates the tracing. And you need to include trcuser.h to use this. There are some settings in trcconfig.h that you need to be aware of. You have to select what hardware port that is used for detailed timestamping. This is actually only used in 2.7, the new version 2.7. You have to specify the FreeRTOS version to make it compile correctly. And then you specify the number of events you want in your buffer and how the buffer should work. If it should be a ring buffer that always keeps the latest events in memory, or if it should stop the recording when the buffer is full. And here is how you use it together with the development boards that you have received. They have an integrated Sega J-Link debugger. And for Sega J-Link debuggers, we have an integration that allows you to download the trace data directly from the board without using IDE if you don't want to. So you select read trace here in the J-Link menu or settings. But if you haven't specified the settings, you will get this dialog directly. So here you have to specify the address of where to begin read the RAM buffer and how much you should read. And this doesn't have to be the exact address of this data structure as long as it fully includes it. So you could, if you want to specify the entire RAM address, but it will take a bit longer to load. If you want to optimize this, you can have a look in the debugger and check these symbols. Here you get the address, and if you check this symbol, you get the size of the data. And if you don't have a J-Link debugger, you can use a RAM dump from just about any debugger, and just open this RAM dump file in the tool. And what I'm really excited about is in the next version, 2.8, that we plan to release in the beginning of next year, we have support for streaming traces. So you only need a small RAM buffer, a few kilobytes, and then you can record for how long you want, many hours if you like. Okay, back to Richard.
Yes, so hopefully you have Atmel Studio installed already, and Johan sent a link to the project, so you should have that as well. If you don't, to say we've got a USB drive here with these on. When you run the demo, the trace buffer will be being created, and then use the trace tool through the menu item that Johan just showed to pull that trace out, see how the tasks are executing, and then there's some very, very small edits to make in that in the instructions. Run it again, pull the trace out, and see the effect that your edits made. But in this demo, what we've looked at is here's the task. It's doing nothing except incrementing a counter. So we've used the parameter here to pass in a variable, and it's casted to a 32-bit pointer, and it's just incrementing that. So this demo task is created 3 times. Remember, each task has its own stack. So we have 3 instances of this task running, each one is incrementing its own variable. And we started off with this task delay commented out. So here we can say we created the same task 3 times, called them different things, D1, D2, and D3. Here we're passing in the variable that it's going to increment, and task 1 priority, task 2 priority, and task 3 priority were all the same. Defined up there, they're all at 0. 0 is important, we'll come to why in a minute when we look at the trace. So the first thing to do was to look at how those tasks executed.
Yes, so in the first case, where we have equal priorities, the scheduler will basically time slice tasks, executing equal amounts of time in each task in a round-robin scheduling manner. In the second case, we have increased the priority of one of the tasks. In this case, it's D3. Since the tasks are never getting blocked, they are running all the time. They want to run all the time. The higher priority task will take over completely and starving out the lower priority ones. They never execute. This red one here is the timer task of FreeRTOS. That is a bit higher priority. Finally, in the third case, we had added the v-task delay call. And now the task will get blocked. And then in the FreeRTOS+Trace, you will now see them as short instances like this. So that each activation, each run between delays is shown as a separate instance, as we say. In this case, we get only one instance for the entire run. Okay.
So one of the things to note in this one is, well, in this one here, the tasks are running all the time even when they're doing nothing. And in this one, we get individual instances, as Johan said. The important thing to note here is this task here, this white task here, which is the idle task, and that's created by the kernel itself. So when these 3 tasks are all blocked, the kernel will run the idle task. One of the things you can see on these 3 scenarios is how, using the real-time operating system, you can create a completely event-driven system. So people will often say, oh, I don't use an operating system because it's too much overhead. In reality, you can actually get a lot more power out of your processor if you stop polling things. In this case, all we were doing was polling time, nothing else, not an input. We were just looking for a time. But all this processing time is being burned up with nothing to do. In this case, the processes or the tasks are only running when they actually have something to do. The rest of the time, they're not doing anything, and you free up a lot of processing time that you can do other things with. Even if your application doesn't have anything else to do, you can use that time to save a lot of power by either just in the idle task saying go to sleep, which is a very crude but effective way of doing it. FreeRTOS also has some specialist low power functionality that allows you to turn the interrupts off as well and set the system into a low power state. So you can start to see some of the benefits of using the kernel here. Oops, that's the wrong thingy. Let's pick that one up. Okay, so now we're going to come on to queues. We only have 40 minutes left. 2 hours is really very, very brief to go over this stuff. So we're just looking at 2 pieces of functionality here. First, tasks, and second, queues. So now we have our tasks. They're running in isolation, that's great, but to make them helpful, they have to interact either with the environment or with each other. What we're looking at here is how they can interact with each other, or actually just one way in which they can interact with each other, and that is through a queue. And a queue is very simply just a way of passing data from one task to another. So again, we have little flowcharts here. It's doing something, it's then going to send data to another task, then do something else, come back up here. So you can imagine it might be processing some kind of input or communications protocol or something. Once it's done the processing, it has a new value, and it wants to send that value to some control task, just as an example of the scenario. This task, on the other hand, doesn't have anything to do until it gets a new value. So it's going to call queueReceive to wait for a value, and it can request to be put into the blocked state until that value is available. So again, this task is not going to use any CPU time until data is available. Then the message comes in, it's going to process it, do something else, and then wait for the next data to come in. So creating a queue, you'll be glad to know, has got a lot less parameters than creating a task. Only two, in fact. The first parameter is the length of the queue. How many items do you want to store in the queue? And this is my very, very crude diagram of a queue. You can see I'm not a graphics designer. And then the second parameter is the amount of data, or the length of each item in bytes of the queue. And in this example, we're just going to be storing a 32-bit variable, that's all. So each one of these buckets here will be 4 bytes long to hold a 32-bit variable. Sending to the queue, incidentally, this is following the same convention. So this function is defined in queue.c. Obviously, you have all the source code, being an open source product, and we want to send the value 10, so we have a variable, value to send, set it to 10, and we're going to send it to the queue. We've just created this queue on the previous slide. Here is a pointer to the data we're going to send, and this is how long we want to wait to try and send. So when we're sending to the queue, if there's space in the queue, in which case there is, because there are 3 spaces and we're all empty, so we've written the value 10 in the front of the queue. It's the front and the back of the queue in this case. We can say, if the queue is full, we're prepared to wait in the blocked state again, so we're not using any CPU time, until either space becomes available in the queue or we time out. So again, it's a very processor efficient way. We're not polling the queue to try and send data at all. It's worth noting also that the data is actually copied into the queue, which is, one possible way of doing this would be to have lots of buffers and then to pass a pointer to a buffer into the queue. Doing it that way means that you've got the person or the task sending to the queue and the task receiving from the queue are sharing a data buffer, and it makes your life a little bit more complex in that you have to decide who is looking after, who's controlling that buffer, who's allocating the buffer, who can access the buffer at any one time, who has to free the buffer. What we're going to do is actually copy data into the queue. So whoever sends to the queue puts the data in the queue, and then it's under the control of the kernel. It can forget about it. Now that's fine when we're sending a 32-bit value. If you're writing a communication stack and you want to send a kilobyte of data, then there is nothing to stop you just queuing a pointer to the data. So rather than saying when you're creating the queue, each item is the size of a 32-bit number, you would say each item is the size of a pointer, and then you just queue a pointer. So you can see by copying by value gives you a much, much simpler interface, but without forcing you to have the overhead of huge buffers if you want to pass lots of data. So you can see here we've In this case, there's only one item put in there, queue send to back. There is a queue send to front as well, but normally you'd say send to back. Now we're going to pass the value 20. So 10 is at the head of the queue and 20 goes behind it. It's like a first in, first out buffer, effectively. The same when we're receiving. This is the same queue. This time, this is a pointer to the place where we want to store the value. So we have a 32-bit number, and we're receiving data into there, and we've read out from the head of the queue, so the 10's gone. It's now stored in our value here, and the 20 is at the head of the queue. This diagram shows 20 being moved up the queue. In reality, of course, it doesn't actually do that. It just moves a pointer to say what the head of the queue is. It doesn't actually copy data around. And again, you can pass in a block time. So if you want to receive from the queue, but the queue is empty, you can say, I want to wait 200 milliseconds, 10 seconds, a year, whatever, for data to arrive, and you will be in the block state, not using any CPU time at all. When you either time out or data arrives, then the kernel will automatically move you back into the ready state, and you just check the return value. If it's true, you've got some new data in here. If it's false, you timed out. So I've given a very basic example of how to use a queue there, and that is to queue a 32-bit number. Most of the time you are going to use it that simply, but the queuing mechanism is actually a very powerful mechanism. For example, in a TCP/IP stack, and we've just released a TCP/IP stack, in fact, it works in this way. We have a task which is controlling the TCP/IP stack. It has to respond to lots of different events. For example, we may have received a new packet from the Ethernet hardware. There are timers which are for ARP processing. You don't have to know what ARP is. It's just something that has to be done periodically. And the application code might have created data that it wants the TCP/IP stack to send onto the network. So the TCP/IP stack waits on a queue, and it receives structures like this. First is the event ID, which might be received data, it might be ARP timer, it might be application TX, transmit, and then it has a second parameter, which is the value. If it's receiving data, the value is set to the buffer that contains the data. If it's an ARP timer, there is no data, so the value is ignored. If the application code is sending data, then the value is set to the data which is being sent out. So you see, the stack checks the ID and then knows how to interpret the value. So it's very, very flexible, very powerful, yet incredibly simple way of doing it. And this is just going back to the state machine. You see, calling queue receive. If there's nothing in the queue and you specified a block time, you will go into the block state and then be moved into the ready state when you time out or data arrives. So the same concept as in the first lab, but now we're actually using real data rather than just waiting for a time. And I think I've mentioned all that already. So, which is good because we can get on to the second lab. So in the second lab, we are going to use... Right, so in this lab, again, it's very, very simplistic lab. We've seen a queue being created and we've blocked on the queues. And we've also, hopefully, if you've managed to complete it, looked at the behavior here. Do you want to describe these?
Yeah, here we see some queue events. Well, we also have some other events here, the state changes in task. We have the transmit task and the receive task. And as you see, what happens is that you make a send operation first, but the transmit task is running at high priority. So it's not received until the transmit task blocks itself by calling retrace delay until. But when it does and control comes over to the receive task, it immediately receives. You have the green one, the green label here means that it was blocked before, and then it will try to receive the next, and then again it gets blocked. And if you double click on any of these events, you get another view showing something like this. Here you see all the events on this particular queue. And it's, in this case, it's very similar, since we only have one queue here. But in other cases where you have many queues, or semaphores or other events, this can be a nice help for analyzing the behavior. And in this view, you can also track the number of messages in the queue. Here's just 1 or 0. And you can also see sequence numbers on messages and automatically find the location where a certain message is sent or received. Yeah, some features there.
So one of the questions I was asked was, what does this sort of hatched bit here mean? So it shows when the task was able to run, when it was moved out of the blocked state. And then when it becomes a solid color is when it's actually executed. So here it's sending to the queue, which unblocked this task, but this task didn't actually start running until that task blocked itself.
Yeah, can you open one? I think you skipped one. Oh, here. So in this case, we've increased the number of messages from 1 to 3, and since the transmit task has a higher priority, it will buffer 3 messages at once. You see here how the buffer increases. We add message number 7, message number 8, and message number 9. And then we let the receive task run by calling the delay function. And then it will then receive message 7, 8, and 9. So, and if we swap the priorities, it will happen then. Now the receive task has higher priority. So whenever you send a task, a message to this queue, the scheduler will notice that this receive task is now ready to execute. It has received a message. There's a message to be received, and it will wake up the receive task, and it will cause contact the task switch over here. Receive task runs and receives it. So for what if the receiver has high priority, it will immediately trigger when there's a message for it. So then we get a quite different picture. Would you like to comment anything here?
No, I think it shows how important it is to choose your task priorities. Again, I always come back to this sort of TCP/IP stack, because it just provides a neat example. One of these tasks might be the TCP/IP stack itself, and it's getting events from the Ethernet interrupts, and it's also getting event in this case being a message on a queue from other tasks, and you can make decisions. If the application is sending occasional data to the TCP/IP stack, you might want the TCP/IP stack to be high priority. So every time it sends a message, it will switch to the TCP/IP stack and send it, if that's what's important to you. On the other hand, if your application tasks are creating bursts of data, most of the time they're doing nothing, and then suddenly it will create 10 messages at once, you might want the application task to be the higher priority, and it will buffer all those messages and only switch to the TCP/IP stack once. Otherwise, you'll get this kind of thrashing behavior of switching between the two. This is why we show these diagrams or try and teach these concepts, so you can get an insight into how your application will run. And using this tool in particular is a very good way of optimizing, because if you've got your priorities in a non-optimal way, for example, you can look at the trace and think, hang on a minute, I can minimize the number of times I'm switching backwards and forwards in these things.